All right, guys, let's look at lesson 1, which is going to talk about nuclear chemistry. Let's review. So we're going to go back in time and we're going to review some things that we've just talked about. So remember, isotopes are atoms that are of the same element that don't have the same number of protons, but different numbers of neutrons or masses. So when we write atomic notation, remember the mass number, which is the number of protons plus neutrons, goes in the upper left-hand corner. You're going to have your element symbol, and then you're going to have your atomic number, or the number of protons or electrons, in the bottom left corner. Remember, you subtract the atomic number from the mass number to find the number of neutrons you have in that atom. So that symbol notation, the atomic symbol notation, is going to be very important when we talk about isotopes that are undergoing nuclear decay, and that is the way that we are going to represent them when you see them. So let's talk about radioactive decay. That is the process by which nuclei emit particles and change into elements, and that is called transmutation, when you change into a new element. This only deals with protons and neutrons because it's what's happening. This process of radioactive decay happens in the nucleus. So the only things that are in the nucleus, like we learned about in the last unit, are protons and neutrons. The identity of the element changes due to the number of protons. We've already talked about this. Elements are specific just for the pure fact of the number of protons that they have. The number of neutrons can change, and that will give it a different mass. But if you change your number of protons, then you're changing the ID of the element and you have a different element altogether. So let's talk about natural radioactivity or transmutation. So this occurs when unstable atoms that are radioactive decay into new atoms. They always turn into a more stable element. So this is due, and the reason why radioactivity happens and atoms decay and that happens is because it's an unbalanced proton-neutron ratio. So the band of stability refers to atoms that are stable due to the proton-neutron ratio. So for example, the best stability to have would be something that would be a 1-to-1 proton-neutron ratio. Atoms that are above the belt have too many neutrons and beta decay due to this. So anything above this belt, so all of this, will undergo beta decay. The beta particle is an electron created when a neutron decays. So for example, we have iodine 131 here. When it undergoes beta decay, it becomes xenon 131 and it eliminates a beta particle. So let's look at examples of beta decay. So thallium 234 undergoes beta decay. So when it undergoes beta decay, what happens is that it releases a beta particle. And since it released a beta particle which has 0 mass and -1 for the atomic number, the total mass on the left side must equal the total mass on the right side. So 234 has to equal 0 plus 234. So the total charge on the left side must equal the total charge on the right side. So thallium had a number of protons of 90. So when it undergoes beta decay, it'll lose -1 plus 91. So when you do 91 minus 1, you get 90. So that's why everything is balanced here. Okay, so we've talked about beta. Now let's look at positron emission. So the atoms below this belt, and this is your belt of stability, the atoms below this belt have too many protons and positron decay. So when you undergo positron decay, a proton turns into a neutron. That is symboled by a B with a plus charge or an E with a plus charge. You'll see both of those when we go over practice examples. So the positron is the opposite of a beta particle. So what happens here is that you will, if carbon undergoes a positron decay, it will become boron, so your atomic number will drop by 1, and your mass will stay the same. So let's look at this example. So K37 undergoes positron decay. So again, this will undergo a decay, so it will break down into two things. The first thing in this equation is a positron particle. We know it's not beta because it has a +1 charge. Beta has a -1 charge. And we know that AR is going to be our new element because we go from an atomic number of 19 to an atomic number of 18. Again, the total mass on the left must equal the total mass on the right. So 37 is on the left. That has to be equal to 0 plus 37 on the right. The total charge on the left must equal the total charge on the right. So 19 has to equal whatever 1 plus 18, 19 is. So let's look at alpha decay. Alpha decay happens when atoms with 82 or more protons will alpha decay. They have too many protons and neutrons. Alpha particles are weak due to their mass, and alpha particles are helium nuclei. So you'll see me refer to this in one of two ways. You'll either see a helium nucleus symbol, which looks like this, or an alpha particle. So when this happens, for example, in this example down here, you have uranium-238 with an atomic number of 92, and it will break down, release an alpha particle. This is an alpha particle. And it will make thallium-90 with a mass of 234. So again, if you undergo alpha decay, you will release an alpha particle plus whatever new nucleus you make. So, and to figure out what is the new nucleus that you make, you just have to do your math. So the total mass on the left, again, must equal the total mass on the right. So 238 has to equal the mass of the alpha particle plus the mass of the new atom that you made. The total charge on the left must equal the total charge on the right. So again, 92 is the atomic number for uranium. That has to equal 2, which goes with your alpha particle, plus whatever your new element is, and in this case, the element that is 90 is thallium. So let's look at gamma decay. Gamma decay is the strongest particle. It accompanies most decays. It's usually not written due to the fact that it cannot change mass or charge of any species, and this is what it looks like. It has 0 mass, 0 charge. We very rarely write it. Gamma decay, for our purposes, is going to be energy. So let's look at Table O and let's look at types of decay. So this is directly from your reference packet. So you have your alpha particle with your 2 notations, your beta particle, your 2 different notations, your gamma radiation. This is how you do a neutron in nuclear chemistry. That's how you signify a neutron. A proton looks like this, and then a positron. Table N looks at decay modes for selected nuclei. So this is a scrunched up version. You have a better version in your actual reference packet, but to fit it on the slide, it's a little scrunched. But these are all your nuclides, your the half-life they normally have, what their decay mode usually is, and what will they decay to. Now let's look at penetrating power. When we look at penetrating power, alpha particles cannot penetrate paper if they're being released from a radioactive source. Beta particles can penetrate paper, but they cannot penetrate aluminum. Gamma rays, on the other hand, can penetrate both paper and aluminum, but are stopped by thick, thick, thick walls of concrete. Radiation is charged, so it can be separated by a magnetic field. So if you have a magnetic field and around this radioactive source, it will break up the alpha particle, the beta particle, and the gamma rays. Alpha particles are positively charged, so they'll go to the negative side of your magnetic field. Gamma rays have no charge, so they'll stay in the middle. And beta particles are negatively charged, so they'll go towards the positive end. Remember, like we talked about in the last unit, opposite charges attract, like charges repel. So let's look at some practice. So complete the example practice problems below showing alpha decay. Remember, charge mass must be conserved. So pause the video, unpause it when you're ready. Great. Well, what did you come up with? Well, these are the answers you should have came up with. So for example number 1, if it undergoes alpha decay, it has to release an alpha particle, which is right here. Now to figure out what else we're missing, 2 plus some number needs to equal 87. So we're going to do the bottom first. 2 plus 85 equals 87. When you look on your periodic table, the element that is 85 is AT. So that's why the element symbol AT is here. 4 plus some number has to equal 220. So 4 plus 216 equals 220. And that's how this is a balanced alpha decay of francium. So let's look at this one. It's undergoing alpha decay, so one of your products needs to be an alpha particle. Again, 2 plus whatever we put here needs to equal 86. We chose 84. The element that's 84 is polonium. And then 4 plus whatever the mass of polonium, it has to be 218 though in order to equal 222. Let's look at these examples. These examples are undergoing beta decay. Pause the video, unpause when you're ready. Great, well, welcome back. What did you come up with? Here are your answers. Now, beta particle decay can be a little bit confusing for students because your atomic number will go up. Your mass doesn't change. As we can see, our mass doesn't change. And our atomic number needs to go up. That's because 16 minus 1 needs to give us 15. So here are your 3 answers for your 3 practice problems. The more you practice these, the easier they will get. So let's look at check your understanding. So complete the example problems below showing positron emission. Remember, charge and mass must be conserved. And we'll check this tomorrow.